Welcome to the Deep Dive, where we take complex information, find the surprising essential insights, and bring them directly to you.
Today, we're embarking on a deep dive into a foundational text. It's in a field that, really, without exaggeration, shapes the modern world all around us.
Absolutely. We're cracking open Elements of Information Theory by Thomas Cover and Joy Thomas. Now look, this isn't exactly light reading, is it?
No, definitely not. It's a go-to for senior undergrads, grad students.
Mhm.
The authors themselves, they describe the math level as reasonably high.
They do, but they also stress the elegance, simplicity, and naturalness of the theory itself.
Which is kind of amazing. And impressively, they managed to build this whole thing largely without needing, deep dives into measure theory.
Which often trips people up in advanced probability.
Exactly. It speaks to the self-contained beauty, I think, of these core ideas.
So our mission in this deep dive is to pull out those core ideas, the fundamental quantities they introduce, and really show how they provide answers. Answers to questions you might not have even realized were part of, well, information theory.
We're looking for the why and the so what.
Yeah, getting to the mathematical essence of information itself. How do we measure it, manipulate it? What are the fundamental limits?
Exactly.
Yeah.
Let's get into this material.
Okay.
So Cover and Thomas, they frame information theory around these fundamental limits.
Mm-hmm.
What are the absolute boundaries on things like communicating data or compressing data,
Mm.
or even areas like statistics and finance.
Right. And they structure the book really well, I think. They introduce these key quantities that, as you read, they feel less like arbitrary definitions
Yeah.
and more like the inevitable answers to these fundamental questions. So what's the first of these essential quantities?
The most well-known is probably entropy, usually written as H,
H.
and you can think of it as the mathematical measure of uncertainty in a random variable.
Uncertainty, like how much surprise there is in the outcome before you actually see it.
Exactly that. If you have a random variable x with a set of possible outcomes, and each outcome has a certain probability, entropy quantifies the average amount of surprise,
Yeah.
or information you get from observing an outcome.
The book gives the formula. It's that sum.
Yeah, the sum involving the probability of each outcome, px, and the logarithm of that probability, log px. Usually log base 2, so we measure in bits.
And the classic example, the one that makes this sort of click for me, is just a fair coin toss.
Perfect example. 2 outcomes, heads or tails, probability half each.
Mm-hmm.
You run the numbers, the entropy is exactly 1 bit.
Which just feels right, doesn't it? 1 bit for yes, no, equally likely outcome.
It does. And the book makes a really powerful statement about this. Entropy is the minimum descriptive complexity of a random variable.
Okay, minimum descriptive complexity. That sounds significant.
It's huge. It tells you, theoretically, the absolute minimum average number of bits you need to encode outcomes from this random variable, no matter how clever your encoding scheme is.
So it's the fundamental limit for compression for that specific data source.
Precisely. H sets the bar for how small you can make your data on average.
Okay, so H is the baseline uncertainty, the compression limit. What's the next key concept they build on?
That would probably be relative entropy. It's also called Kullback-Leibler divergence, or KL divergence,
Right.
often written DPQ.
DPQ. And this measures the difference or divergence between two probability distributions, P and Q.
That's right. It's a way to quantify how different two probability distributions are.
So is it kind of like a distance between two different ways data might be generated?
Conceptually, sort of, yes, but there's a crucial difference from a typical distance metric. It pops up naturally in problems like hypothesis testing. Say you're trying to figure out if your data came from distribution P or distribution Q. Relative entropy helps tell you how quickly or how easily you can distinguish between the two based on the data you collect.
So a higher DPQ means P and Q are more, well, distinguishable.
Exactly. Easier to tell apart.
And you said it's not a true distance. Why not?
Right. So while DP2 is always non-negative, and it's 0, only if P actually equals Q, it's not symmetric.
Not symmetric, meaning DPQ isn't the same as DQ.
Generally, no. The book gives examples. And that asymmetry matters.
How so?
Well, it means interpreting it simply as distance can be a bit misleading. It's more about the inefficiency or the information loss, maybe, of assuming the distribution is Q when it's actually P.
Or vice versa.
Right. The cost of being wrong depends on which one is the true distribution and which one is your model. That's where the asymmetry comes in.
Okay, so divergence, not quite distance. Got it. What about mutual information?
Yeah.
That sounds like it has to be about shared knowledge or connection.
Precisely. Mutual information, usually I, X, Y, quantifies how much information knowing one random variable, say y, gives you about another random variable, x.
Ah, so it's the reduction in uncertainty about X that you get by observing Y.
Exactly. How much less surprised you are about x once you find out what y is.
Okay.
And here's where its fundamental nature really, really shines. Mutual information arises as the maximum achievable communication rate you can get between a source and a destination when there's noise involved.
The communication rate, so like channel capacity.
Yes, this is the absolute backbone of understanding channel capacity. It defines it.
And this is also where the book throws in that kind of curveball connection, right? The gambling thing.
Yes. That mutual information also corresponds to the increase in the doubling rate of wealth if you have side information.
Okay, that's unexpected. Information theory making money.
It's one of the striking insights in the book, that connection between information flow in communication and the value of information in, say, investment or gambling. We'll definitely loop back to that. It's fascinating.
Absolutely. So, okay, we've got entropy, uncertainty, compression limit, relative entropy, distribution divergence, hypothesis testing, and mutual information, shared info, communication rate, gambling gain. These feel like the fundamental building blocks.
They really are. And the book shows they have these elegant relationships between them, like chain rules.
Chain rule.
Yeah, ways to break down the entropy or the mutual information of a whole set of variables based on their conditional dependencies. How the uncertainty of x and y together relates to the uncertainty of x plus the uncertainty of y given x, things like that.
Okay, neat algebraic structures. So let's see these concepts in action. First up, data compression. How does information theory tell us the limits there?
Right. So the goal is simple. Represent information using the fewest possible bits, but still be able to get the original back perfectly.
And entropy H gives us that theoretical minimum average number of bits needed.
Exactly. That's the floor. Now, any instantaneous code.
Instantaneous meaning you can decode a symbol as soon as its code word arrives. You don't need to wait for the next one.
Precisely. No code word is a prefix of another one. For any code like that, the average length of your code words, L, has to be greater than or equal to the entropy, Hx.
LEHX.
Yep. And this is directly tied to the Kraft inequality. It's a mathematical constraint on the lengths you can even possibly assign to code words in a prefix-free code.
Okay, so theory sets the limit. What about actually doing it? Practical methods.
Well, the book explores practical coding schemes. Huffman coding is the classic example.
Ah, yes, Huffman coding. I remember that from computer science.
Right. If you know the probability distribution of your source symbols, Huffman coding gives you a provably optimal prefix code. It minimizes the average code word length. It gets as close to the entropy limit as you can with that kind of symbol-by-symbol approach.
So it's the best you can do if you know the stats.
For that type of code, yes. They also mentioned Shannon-Fano-Elias coding, which is maybe conceptually a bit simpler, a precursor. It guarantees you get within, I think, 2 bits of the entropy.
Well, pretty good.
Yeah, and the ideas behind that lead into arithmetic coding, which is incredibly powerful and forms the basis for a lot of modern compression standards you use every day, like in JPEGs or FAX machines.
Right, right. But what if you don't know the probabilities of your data source beforehand, which is usually the case, right?
Often, yes. And that's where universal source coding comes in. The Lempel-Ziv algorithms are the prime examples here, LZ77, LZ78.
Lempel-Ziv, like the compression used in GIF files, or old dial-up modems, stuff like PKZIB.
Exactly that lineage. These algorithms are clever because they don't need to know the source distribution in advance.
How do they work then?
They essentially work by finding patterns, specifically repeated sequences or phrases, in the data stream as they go along. They parse the input into phrases and encode them by pointing back to where that phrase appeared earlier.
Ah, so they kind of learn the structure of the data while they're compressing it.
Precisely. They adapt.
Yeah.
And the key thing is their asymptotic optimality, meaning as the length of the data sequence gets really, really large, their compression rate actually approaches the true entropy rate of the source.
Even though the algorithm didn't know the source statistics when it started.
Exactly. That's what makes them universal and so powerful for compressing unknown data streams, like text or executable files or whatever.
Okay, that's really cool. So that takes us from compressing the source to the challenge of actually sending it somewhere, possibly through noise. Let's talk about communication channels.
Right. This is where the concept of channel capacity, C, becomes the absolute fundamental limit.
Capacity, the maximum rate, bits per second or bits per channel use?
Bits per channel use, typically. It's the maximum rate at which you can transmit information over a noisy channel and still be able to achieve an arbitrarily small probability of error at the receiver.
So it's the ultimate speed limit for reliable communication over that specific link. No matter how clever your error correction is, you can't beat C.
You cannot reliably transmit faster than C. That's the limit. And capacity itself is defined using mutual information.
Ah, back to mutual information.
Yep. It's the maximum possible mutual information between the channel's input and its output, where you maximize over all the possible ways you could distribute the input signals, finding the best way to talk to the channel to get the most information through.
Okay, examples really help here. The book has the noisy typewriter one.
That's a great one. Imagine a typewriter, 26-letter keys. When you hit a letter, it either types that letter correctly or it types the next letter in the alphabet, each with 50% probability.
Okay, so A gives you A or B. B gives you B or C and so on. Z gives you Z or A.
Right. What's the capacity of that channel? It turns out to be log base 2 of 13 bits per character typed.
Log 13. Why 13? There are 26 letters.
Because you can be clever about which letters you choose to send. If you only ever send, say, A, C, E, and so on, every other letter,
Okay.
then hitting A gives A or B. Hitting C gives C or D. Hitting E gives E or F. Notice the pairs of possible outputs are disjoint.
Ah, so if the receiver sees a B, they know for sure you must have typed A. If they see a C, you must have typed C.
Exactly. By only using those 13 input letters, you've created 13 distinguishable pairs of outputs. You can effectively send one of 13 messages perfectly reliably over this noisy channel. The capacity is log base 2 of 13.
That is clever. Okay. And the simplest error model is the binary symmetric channel, the BSC.
Yep. Just bits going in, bits coming out. Each bit has a fixed probability P of being flipped to the opposite value during transmission.
0 becomes 1, 1 becomes 0 with probability P.
Right. And information theory proves, maybe counterintuitively at first, that you can still achieve reliable communication at a positive rate over this inherently unreliable channel.
Right.
As long as P isn't 0.5, of course.
If P is 0.5, the output is pure noise, tells you nothing about the input.
Right. But for any P less than a 0.5, there's a non-zero capacity. You can send data reliably.
And the proof that this is even possible, that's the big one, the channel coding theorem.
One of the crown jewels of the theory, absolutely. Shannon's masterpiece. It mathematically proves that for any rate R, that is below the channel capacity C,
So RSTU.
dot codes exist that allow you to send information with an error probability that can be made arbitrarily small, vanishingly small, just by using longer and longer blocks of code symbols.
Wow. So it guarantees these amazing codes exist, but does it tell you how to build them?
Not directly, no. It's often an existence proof, sometimes based on averaging over random codes. It tells you good codes are out there, and probably lots of them, but finding them efficiently and constructing them, that's the whole field of coding theory that came after.
Right. Though the book does mention structured codes like Hamming codes, right, as early practical examples.
Yes, Hamming codes are a great example of algebraic codes designed specifically to detect and correct a certain number of errors. They're not necessarily capacity achieving, but they were a breakthrough in practical error correction.
Okay. Now, there's another result in the book about channels that feels wrong somehow. The idea that feedback doesn't help capacity.
Yes. For discrete memoryless channel, a DMC, the capacity with feedback from the receiver back to the transmitter is the same as the capacity without feedback, CFB-Phi.
But that seems crazy. Surely if the sender knows what the receiver actually got or knows if there was an error, they could adapt and send more effectively, like asking, did you get that?
You'd absolutely think so. And feedback is useful in practice. It can simplify the encoder or decoder design significantly. It can allow for things like automatic repeat requests, ARQ, or adapting the transmission rate.
But it doesn't increase the fundamental limit, the absolute maximum rate.
For this class of channels, no. It doesn't increase the maximum mutual information you can squeeze between input and output. That limit C stays the same. It's a surprising result.
It really is. Okay, fascinating. And then there's the source channel separation theorem. What's that about?
This is another cornerstone result, especially for system design. It basically states that for standard point-to-point communication,
One sender, one receiver.
you can optimally design your data compression system, your source code and your error correction system, your channel code, completely independently of each other. And if you just chain them together, compress first, then add error correction, the overall system can achieve the theoretical optimum.
So you can solve the compression problem aiming for the entropy H, then solve the channel problem aiming for capacity C, stick them together, and that's as good as any single complicated integrated approach could ever be.
Yes, in this basic fundamental setting, separation holds. Compress optimally, then encode optimally for the channel. Job done.
That simplifies things hugely from an engineering perspective.
It does, although the book is careful to point out it includes examples where this separation might seem a bit misleading, maybe.
Like what?
Like sending something with inherent structure, like English text or maybe speech, over certain channels. The natural redundancy in the source itself seems like it could potentially help directly with error correction, you know?
Maybe you don't need to compress it all the way down to pure randomness first.
Right. It hints at the subtleties and more advanced topics in network information theory, or situations with delay constraints, where strict separation might not always be the absolute best or only way to think about things.
Yeah.
But for the baseline, it's a hugely important principle.
Okay. So we've quantified information, figured out how to compress it to its limit, and how to send it reliably near the channel's limit, even with noise. But the book really takes these ideas into some unexpected territory after that.
It really does. Remember that mutual information and wealth connection we mentioned?
The gambling link.
The book has a whole fascinating chapter on gambling and portfolio theory.
Seriously. How can information theory help you, make money at the racetrack or in the stock market?
Well, it's about identifying strategies that maximize the long-term growth rate of your wealth. They show this deep duality between the entropy rate of a market. Think of it as the unpredictability of horse race outcomes, perhaps, and the maximum possible growth rate of your wealth if you invest in that market. And they introduce the log optimal portfolio strategy. This strategy says you should bet on each possible outcome, like each horse in a race, in proportion to its true probability of winning.
So if a horse has a 20% chance of winning, you allocate 20% of your current capital to betting on it, assuming you know the true probabilities, of course.
Exactly. If you can do that, and you rebalance your bets according to those probabilities for every race or every investment period, this strategy is proven to maximize the doubling rate of your capital over the long run. Your wealth grows exponentially faster than with any other strategy, asymptotically.
Geometrically faster. Wow. So it's not about winning big on one bet, but maximizing long-term growth.
Precisely. And now, what about side information? What if you get a tip before the race?
Yeah.
The increase in your maximum possible wealth doubling rate that you get from having that side information, it's exactly equal to the mutual information between the race outcome and the side information you received.
Whoa. So outcome, side info, directly translates into faster potential wealth growth.
Directly. More relevant information means potentially faster exponential growth in this idealized model. It's a really powerful, tangible link between bits of information and potential financial value.
That is amazing. What else? Where else do these ideas pop up?
Well, the book also applies these concepts just to analyze language itself, looking at the entropy of English text.
How predictable is English?
Kind of. By building probabilistic models, looking at letter frequencies or frequencies of pairs of letters, diagrams, or even words, and estimating those probabilities from huge amounts of text, you can estimate the entropy rate. How much information, on average, does each letter carry, given the context?
Trying to quantify the redundancy in the language.
Exactly. And then there's statistics. Information theory provides some really fundamental limits and tools there, too.
How so?
Well, we already saw relative entropy showing up in hypothesis, testing how distinguishable are two statistical hypotheses. But there's more. Concepts like Fisher information.
Fisher information, okay.
Which measures how much information a random sample carries about an unknown parameter you're trying to estimate. And this leads directly to the Kramer-Rao inequality.
The Kramer-Rao bound.
Yes. It gives a fundamental lower bound on the variance or the uncertainty of any unbiased estimator for that parameter. It essentially says, based on the Fisher information in your data, here's the absolute best precision you could possibly hope to achieve when estimating that parameter. You can't do better.
So it quantifies the limits of statistical inference based on the information content of the data itself.
Precisely. The book also touches on the method of types.
Method of types.
It's a way of analyzing long sequences of data by looking at their empirical probability distribution, just counting the frequencies of symbols in the sequence you actually observed. This type tells you a lot about the sequence, and this connects to Sanoff's theorem, which deals with large deviations. How unlikely is it to observe a sequence whose type is very different from the true, underlying probability distribution of the source.
Okay, so analyzing sequences by their statistical fingerprint.
Kind of, yeah. And then there's this really deep and fascinating connection to the very nature of complexity itself through Kolmogorov complexity.
Kolmogorov complexity, that sounds fundamental.
It is. The Kolmogorov complexity of a string, say a sequence of bits, is defined as the length of the shortest possible computer program that can generate that string and then halt using some fixed universal computer.
The shortest description, like the ultimate compressed version of that specific string.
Exactly. It's the theoretical minimum description length for that individual string. It measures the string's inherent algorithmic randomness or structure.
How does that work? Give me an example.
Okay, think of a string like 010101 repeated a million times. The Kolmogorov complexity is very small because a short program can just say print 01 a million times.
Right.
But now think of a truly random string of a million bits, like from a perfect coin toss. The shortest program to generate that specific string is likely just the program that contains the string itself.
Yeah.
Print this exact million-bit sequence.
So its Kolmogorov complexity is roughly the length of the string itself. High complexity means high randomness.
Basically, yes. And the amazing connection is back to Shannon entropy. A fundamental result shows that the expected value of the Kolmogorov complexity, averaged over all strings generated by a random source, is very close to the Shannon entropy of that source.
Wow, so the average algorithmic complexity matches the average information content defined by Shannon.
It links the complexity of individual instances to the statistical average complexity. It's a profound bridge.
And this leads somewhere practical, right? Like Occam's razor.
Exactly. It leads directly to the minimum description length, MDL principle. MDL provides a formal information theoretic foundation for Occam's razor, the idea that all else being equal, the simplest explanation is usually the best one.
How does MDL formalize that?
In MDL, you judge a scientific model or a statistical model based on how well it allows you to compress the observed data. The best model for a given data set is one that minimizes the total description length.
Total description length.
Which is the length of the description of the model itself, plus the length of the description of the data when encoded using that model.
So you're trading off model complexity against how well the model fits the data.
Precisely. A very complex model might fit the data perfectly, so the data description length given the model is near zero. But the model description itself is very long.
While a very simple model is short to describe.
But it might not fit the data well, requiring a long description for the deviations, the errors, the residual information in the data that the model doesn't explain.
So MDL says find the sweet spot, the model that gives the best overall compression of both theory and evidence.
That's the idea. It's a powerful principle for model selection in statistics and machine learning.
Okay. And finally, the book doesn't just stop at point-to-point communication. It ventures into network information theory.
Right, moving beyond just one sender and one receiver, thinking about scenarios with multiple users interacting.
Like what kind of scenarios?
Well, they introduce problems like the multiple access channel, MAC. Think of several people trying to talk to one central base station, like cell phones talking to a tower.
Okay, multiple senders, one receiver.
Or the broadcast channel, BC. That's one sender trying to transmit information to multiple receivers simultaneously. Maybe different information for different receivers, or common information for all.
Like a radio station, or maybe a teacher in a classroom trying to reach students with different levels of understanding.
Exactly. And the relay channel, where information gets from a source to a destination by being passed through intermediate nodes, or relays.
Like nodes in the internet, maybe?
Could be, yeah. These network scenarios are much more complex than point-to-point, and finding the capacity regions is often extremely difficult. Many are still open research problems.
But they introduce some key results, like Sleepy and Wolf coding.
Yes, Sleepy and Wolf is fascinating. It deals with compressing correlated sources.
Correlated sources? Like what?
Imagine you have two sources, X and Y, that are generated separately but are statistically related. Maybe X is the temperature reading from a sensor here, and Y is from another sensor nearby. Or left and right channels of stereo audio, they aren't independent.
Okay.
Sleepy and Wolf coding shows how you can compress X and Y individually at separate encoders, send the compressed streams over the network.
So X's encoder doesn't see Y, and Y's encoder doesn't see X.
Right. And then have a joint decoder at the receiver that gets both compressed streams and can reconstruct both X and Y perfectly.
Okay. And what's the surprising part?
The surprising part is the compression rates you need. You don't need to compress X at its full entropy Hx and Y at its full entropy Hy, as if you wanted to decode them independently.
You can do better.
Yes, because the joint decoder can use the information in the Y stream to help decode the X stream and vice versa, exploiting the correlation. The required rates, Rx and Ry, only need to satisfy constraints involving the conditional entropies, like Rx needs to be at least Hxy, the uncertainty remaining in X given Y.
And Ry at least Hyx.
And the sum rate, Rx plus Ry, needs to be at least the joint entropy, Hy. But crucially, Hy is less than Hx if they're correlated, so you save bits compared to compressing them totally independently.
That feels like pure information efficiency in action. Because the decoder sees both, it can leverage the redundancy between them, meaning the individual compression didn't have to be quite so aggressive.
Precisely. It's a beautiful demonstration of how correlation fundamentally impacts the limits of distributed data compression.
Wow. Okay, so we've really taken a deep dive into Cover and Thomas's elements of information theory. We pulled out these core concepts: entropy, relative entropy, mutual information.
The fundamental currencies of information.
And I've seen how they set the absolute limits for practical things like data compression and reliable communication over noisy channels, Huffman, Ziv, channel capacity.
Yeah, the engineering foundations, but then also how these same quantities, these same ideas, just keep popping up in fields you might not immediately connect.
Right, from figuring out the optimal way to grow wealth in gambling or financial markets,
To putting bounds on statistical estimation, quantifying how much information is in your data.
and even providing this formal underpinning for Occam's razor through the minimum description length principle, selecting the simplest, most compressive model.
It's truly remarkable, isn't it, that a field really born from very practical engineering problems in telegraphy and telephony
Yeah, how to send messages efficiently and reliably.
ends up providing such universal principles. Principles for understanding information, uncertainty, complexity, inference across so many different domains.
It really suggests these aren't just, engineering tricks. They feel more like fundamental properties of how information itself behaves in the universe.
They give us the mathematical language to understand the basic currency of the digital age, and maybe even more broadly than that.
So what does this all mean for you listening? Well, think about this for a moment. That idea from the gambling and portfolio section, the concept of universal portfolios.
Yeah, the extension of log optimal betting.
It suggests that even if you don't know the true market probabilities, you can still devise investment strategies. Strategies that, over the long run, will achieve essentially the same exponential wealth growth rate as the best, constant, rebalanced portfolio you could have possibly chosen in hindsight.
It's almost like achieving retrospective optimality, asymptotically, without needing a crystal ball. Just by intelligently processing the sequence of market data as it arrives, using algorithms inspired by these universal compression ideas.
A strategy that doesn't require perfect foresight, just the correct application, maybe implicitly, of these deep information principles. Food for thought.
Definitely. Keep exploring how information shapes the world around you.